A pipeline to carry 1 million barrels per day of crude oil. They give you that 1 barrel is equal to 42 gallons, specific gravity, and the viscosity. It's constructed with a 50-inch inside diameter commercial steel pipe, and it's 700 miles long. The source and destination are both at atmospheric pressure, and they were nice, it's at the same elevation. In this pipeline there are 50 wide open gate valves, 25 half open globe valves, 50 45-degree elbows. There will be 25 identical pumps along this pipeline, each with an efficiency of 70%. What is the power required for each pump? And so I've assembled the information here. Note that when I believe the cutoff is something like 14 inches for nominal being the same as actual inner diameter, we're told this is the actual inside diameter is 50 inches. This is commercial steel pipe, and so I have the roughness here at 0.0018 inches. This you can look up in various tables, whether your textbook or Perry's handbook. Length of pipe is 700 miles. Density, using water, nominal value of water as the reference, so 0.9 times that. Centipoise we need to define in MathCAD, so the viscosity is 25 centipoise. Remember, water is 1 centipoise, so this is a little bit more viscous than water, quite a bit more viscous than water. And now we have some fittings and valves and things like that that we need to account for. So the number of open gate valves I've set at 50. Number of half open globe valves is 25. 45 degrees elbows is 50. There are 25 pumps. We're not just having a couple pumps pumping this stuff for 700 miles. The efficiency of each of those pumps is given, and then some information about the flow rate. So 1 million barrels per day is 4.42 million gallons per day. So what is the power required for each pump? That is what we're asked to calculate. So I don't have a nice schematic drawn out for you. I mean, this is just a pipe where you've got, again, the inlet and outlet pressure are both at atmospheric pressure, and I think you can just visualize pumps in a pipeline pretty well. So I should have drawn a nice little diagram, but I didn't have time to do that. So what we can do though is we can realize that we need to set up an energy balance on this. And so we are going to have the inlet, have position 1 be the start of the pipeline and position 2 be the end of the pipeline. And so I have written the general Bernoulli equation, and we can go through and we can start talking about how we can simplify this equation. So the source and destination, they are both at atmospheric pressure. So these pressure terms are going to cancel. What about the velocity terms? We do have a finite velocity, but we are assuming that this is a constant 50 inch inside diameter pipeline, not changing from the beginning to the end. So these velocity heads are going to cancel. What about the elevation? Elevations are the same. Elevations cancel. Head extracted. Is there any head being extracted? No. That term goes away. And so what we're left with a pretty simple equation of the head loss being equal to the head added. And that is this equation right here. So head added, and this is from our pumps, is going to equal to the head loss due to the friction of flow in our system. The head loss is going to be equal to this equation here, and there's several ways you can express this in terms of volumetric flow rate or linear velocity. In this case, I mean, it really doesn't matter. I've given it to you as linear velocity here. I think maybe later we might use the volumetric term, but If you look in your textbooks or reference books, you'll find the different forms. The one thing is, though, again, I like having the head loss in terms of per unit weight. And so if you look in your textbook, they will not have G. They write it on an energy per mass. I like to use energy per weight because of the form of the Bernoulli equation that I like working with. Anyway, so this is what we have to deal with. We have to calculate the total head added and then basically factor in efficiency and consider that, and then divide it by 25 pumps. Now, this head loss, there's a couple different ways that you can calculate head losses. One of the ways is by using the equivalent length. And I kind of prefer that. I kind of prefer using the equivalent length. I think in some cases it's easier, but there will be cases where a velocity head loss will be what you want to use. But let's use the equivalent length method to calculate the head loss. And so what that means is that for all of these valves and elbows, we need to figure out what the equivalent length of those are from the tables that are given to us in our reference books or textbooks, and we're going to add that to the actual length of our piping. So in our head loss, we will have this L equivalent will be the equivalent length from all these valves and elbows plus the actual 700 miles. So in your textbook, those equivalent lengths are given to you in table 19.2, and you can go to a number of different reference books. I'm sure in Perry's and other handbooks you can find what these equivalent lengths are equal to, and they are always, remember, they are always written and given to you in the tables in terms of with respect to the inner diameter. So the length of the pipe, of course, is given at 700 miles. What about open gate valves? Well, if you look at the value in table 19.2, you see that the equivalent length for an open gate valve is equal to 9 times the pipe diameter. And so then we just multiply by the number to get the total equivalent length for our system. So the number of open gate valves was 50, right? And so we do that, and we see that the equivalent length of all those gate valves is 1,875 feet. That means that these gate valves provide the frictional resistance that 1,875 feet of just regular 50-inch piping would provide. So that's quite a bit of that's quite a bit of resistance. What about globe valves? You'll see the globe valves are even bigger, right? Globe valves, if you look at their inner mechanism, they have a lot more resistance to flow, 475 times the ID, and then we multiply by the number, we get almost 50,000 feet of, so how many miles is that? Maybe 7 miles worth of frictional resistance. And then the elbows, not quite as much, but still you see it's somewhat significant. All right. Another thing that we'll have to recognize is that generally these systems, we're going to have a supply tank and a destination tank. So when you have a supply tank, you are going from this, maybe why we should have a schematic in here, but when you have a supply tank, you are going from a very large cross-sectional area to a very small in the tank to a very small cross-sectional area for the relatively small cross-sectional area for the pipe that's come in. So that's a contraction. And so you look up the contraction, that is 27.5 times the diameter. And then at the end of our system, we're going to be going into a destination tank. So that's going to be an expansion. And so that's going to be 50 times the inner diameter. So you see, it's not nearly the order of magnitude, it's a full order of magnitude below the frictional losses that you would find for the valves in the elbows, but it does add something to the equation. So what we can do here is we can sum up the total equivalent lengths and you can see here the total equivalent lengths when we take into account the actual pipe and then all of these fittings, expansions, contractions, you get about 3.7, 3.8 million feet of equivalent length. Now, that is going to go here. All right. What we also need to calculate is the fanning friction factor. So, for the fanning friction factor, that means we're going to need to calculate the Reynolds number. Flow in a circular pipe, for calculating the Reynolds number, we can either use the linear velocity or we can use the volumetric flow rate because we have a circular pipe. And so to make things a little easier, I just did the volumetric flow rate formula. You see we get a Reynolds number of 66,000. So that is definitely turbulent flow. So that's one thing you need to be careful of when you're dealing with these higher viscosity liquids, is that you may run into cases where you have laminar flow, but in this case we are flowing fast enough that we still have turbulent flow for this viscous oil. I then calculated the cross-sectional area, pretty big pipes here, and then calculate the linear velocity. We will need that linear velocity up here as well. So Reynolds number first, linear velocity, or it really doesn't matter how you do it, but we get the Reynolds number, we get the linear velocity. Now we're almost on our way to doing the fanning friction factor. And so the fanning friction factor, if you really want to use charts, knock yourself out. You're not going to be as accurate. It's really better, and I strongly recommend that you use calculation tools like MathCAD or other calculation tools to make these things a little bit easier. Plugging these things into a calculator can be somewhat tedious. So you take the fanning friction factor equation, solve it for F, and this is what you get. Remember E, that's the roughness of the pipe. That is a constant that we looked up. ID, of course, the inner diameter, and the Reynolds number that we just calculated. We get our fanning friction factor of about 4.89 times 10 to the minus 3. It's dimensionless. And if we have done lots of these kinds of calculations, we realize that this is a reasonable value for the fanning friction factor. Now, if you think about it, we have calculated everything, we know everything to calculate the total head loss in this equation. So we put all this together, we calculate the total head loss, 2 times the fanning friction factor times equivalent length times linear velocity squared, divided by the inner diameter, and G is in here because this is on a per weight basis. Our total head loss on a per weight basis, energy per weight basis, is about 6,220 feet. So notice our equivalent length was millions of feet, but the equivalent length is only part of the head loss calculation. So 6,220 feet of head loss. Now what we need to do is, of course, we can calculate the total amount of head that needs to be added to this oil, and so that is just equal to the head loss. So this is how much head needs to be added. This is the actual energy added per mass of oil flowing through our pipeline. We then calculate the power. Remember, to get power from head, we take the head and multiply by rho GQ. Density, gravitation constant, times the volumetric flow rate. So we've already calculated the volumetric flow rate. We're given to that in the, what was it, million barrels per day. Also notice that I am dividing, right now I am dividing by the efficiency. All right. This is a total power over all those pumps. We're assuming all those pumps have the same efficiency. I believe it was 70 or 80%. 70%. So I'm going ahead and I'm dividing by that efficiency now for the total power. And so we get what? Almost 60,000 horsepower. That's a lot of horsepower. But remember, we're going to be dividing that up among 25 pumps, and so we take that total horsepower, we divide by the number of pumps, and for each pump that comes up to about pretty close to 2,400 horsepower. So that is, and that's our answer, about 2,400 horsepower. Now that's, according to our problem, that's the minimum amount we would need. Notice that one of the things that I want to emphasize is that when you have any kind of pumping applications, you're dealing with equipment that tends to wear out pretty quickly, and if a pump goes down, then your whole pipeline goes down. And so for almost every pumping application that you have in industry, you always have a backup pump. And so they say 25 pumps. I'm assuming they mean these are the primary pumps. Each pumping station along this pipeline would have at least one backup pump. And you would also should note that there will probably be a little bit of extra frictional losses because of all the piping. Whether or not that's included in their original estimates of these in the problem statement, I'm not sure, but that is something that you would want to consider. Also, for pumping crude oil like this, you would want to be concerned with the fouling inside of the pipes, and you would probably want to boost your pumping power maybe even a little more, because of course the faster you flow, the less fouling and scale and buildup you'll have inside the pipelines, and hopefully your system will stay up and running for longer. Now, the next thing that I want to do is I wanted to look at the we use the equivalent length method for the head loss. You can also use the velocity head method, and so this is covered in your textbook and you can read through this, but you use a different table to look up what's called the K factors for the velocity head. And so we look up the K factors for the 45-degree elbow. You can see it's 0.35. The half globe, that's a lot bigger because it has a lot more tortuosity through a globe valve than other valves, and so that's 9.5, 0.17 for an open gate, and then a contraction is 0.55, and an expansion is 1. For a pipe, the K value for a straight pipe is just 4 times the fanning friction factor times the actual length of the pipe divided by the inner diameter. And so we calculated the fanning friction factor above. We know this is 700 miles and this is 50 inches. And so then what we do is we multiply that by u squared over 2g. We sum up the K values, and in this case we have multiple pieces, multiple units for some of these fittings. And so we sum that up, and our head loss in terms calculated from the velocity head method is 6,222 feet. What did we get when we used the equivalent length? Our head loss was 6,220 feet. So that is pretty darn close. That's within three significant figures is the same number, and that is definitely close enough for the kind of work we do. So we essentially get the same answer whether or not you use the equivalent length or the velocity head method.